Uh, we are going to start the lecture 3 for day 1, which will be mostly the modeling characteristics and application of fuel cell. So mostly the theory part you understood, and fuel cell chemicals and all those involved chemical reactions. And now mostly the modeling aspect we'll be discussing in this third lecture. Over to you, Professor.
So, this section we may mostly talk about the modeling, because we already talk about the applications. I am not going to repeat it, but we mostly talk about fuel cell modeling. Now, when you talk about the modeling, that means that we are talking about the mathematics and simulation based representation of fuel cell behavior. Like, if you remember that we shown like IV curves, the relation between voltage and current, and also it could be relation between voltage, power, and so on. So, if we want to exactly replicate that behavior, we need to develop the model, because at then as an engineer we always look for the differential algebraic equation, and using that we do all sort of studies. And you want to do anything like the system design, control, optimization, system integration, or even like integrating in the vehicle. So, the first requirement that you have to have accurate modeling. Unless you have got accurate modeling, whatever control, design, optimization you are going to do, and if you implement in the real system, you are not going to get your desired performance. So, that is why modeling is quite important, and again model actually involves different level of details, like the electrode, electrolyte, either it is a single cell or stack, or even the system level. And why it is important to do the modeling? Because if you want to predict like whatever voltage, current, power you are going to get from the system, you need to do the modeling. And also if you want to analyze the efficiency, so we did mention like that 40%, 60%, 50% efficiency, but that is the standard one. But when you are going to design something and use for particular application, you might not get your desired efficiency, right? And if you want to determine by yourself, you have to have the modeling, and then you can analyze efficiency. You can analyze what sort of fuel consumption be like for a particular fuel cell for a particular application. So, to understand the level of fuel cell that you need for a particular application. So, let us say you for example have 5 kilowatt electrolyzer in a lab or in your building, and you want to know like what sort of fuel I need for using for a particular period of time, or to supply load for a particular application. So, that is why you need the modeling. And if you want to design control, the first thing as you know that we need to know the modeling. If you want to optimize the thermal, water, and fuel management, also you need the modeling. And later if you want to facilitate the system integration with power electronics, inverter, converter, even like if you want to add additional battery, that also we need to do the modeling first and see like the system response, and then we can like in the either real application or laboratory environment, we can make the real system. And definitely the modeling enable like real time simulation using the hardware loop as well. So, that is also to do that also you need the modeling. Now, there are for fuel cell in the literature mostly 4 different types of model available, and the first one we call it empirical models. So, the empirical model mainly based on your experimental studies. So, you do experiment, you measure some variables or some parameters, and then using that one you use curve fitting method to exactly analyze the system behavior. But here we don't depend on the system either physical or circuit model. We just measure some parameter, and using that one by trial and error method we develop the curve fitting, using curve fitting the model, and then we using that model. So, mainly when I say the model, mainly this one like the voltage current relationship from your test data, but we don't use like any physical model or electrical equivalent circuit model. Just from like experiment you can get that empirical simple model, and whatever like model that data that you collect, and using the curve fitting method, at then you are going to get a equation something like that, which again represent the typical typical like the voltage equation. Now the next one, so the next one is like semi empirical. So, semi empirical means that you are combining empirical, but at the same time you are also considering like that some physical characteristic of the system, and that physical characteristics actually normally like if it is a cell level, then we use like this equation, but we can also use the stack level equation as well. Now, what we do, we normally start with here this characteristic equation, and then after that we use the empirical like your data from experiment, just to better tune the system to get exact like system behavior. And this equation again, if you can remember that we talked about that IV curve, where in the IV curve we have got three regions like activation, ohmic and concentration, and these three nothing but the losses, right. So, whatever internally voltage you getting from the cell, and if you subtract these three losses, you are going to get the cell output voltage. Now, the third one we called it like physics based or detailed like the dynamic model. So, this one actually consider not only like the electrochemical that I mentioned previously. So, this one just like the electrochemical, but it does consider like thermal and also fluid, anode, cathode, all the dynamics. So, if you remember, there is some reaction happening in the anode, some reaction happening in the cathode, and also like heat flow, water flow. So, if we combine all this dynamics, then we are going to get that detailed physics based full dynamic model, and it capture the transient behavior, the temperature gradient, water transport, fuel, air flows, everything. But the other model that I mentioned previously, it does not include temperature changes, it just consider constant temperature, and then constant water flow, constant air flow. So, it does not consider any changes, all those parameters. But it does require like significant computational resources, because you are considering so many nonlinear model that require computational power to solve it, but it definitely better and more accurate than other method. If you want to do like detailed system level design, system level optimization, and further academic research. Also it depends like what type of research. Some research might be enough just considering the simple equivalent circuit as well. And the final one, what we do, we like develop the equivalent circuit of the fuel cell, and then from that we develop the using like KVL, KCL, like Kirchhoff voltage law, current law. From that actually we develop the model. And this is like all the parameters that actually you need if you want to do fuel cell modeling. So, you need the cell voltage, current, temperature, fuel and oxidant flow rates, like humidity level, pressure effect, internal resistance, losses, hydrogen and air utilization rates, heat and water management. So, this one actually for the detailed model that I mentioned, but what happened in many cases, it is not easy to get all the data you need for a particular system. So, that is why I mean in many cases, that is why I mean we like we had to consider constant and neglect many parameters. But as I mentioned, like depending on the application, sometime simple model will be more than enough, because it is going to reduce your computational power as well as computational complexity as well. And normally like in terms of software, I mean MATLAB Simulink, I mean for control design, system simulation, real time testing, you can use that. But if you want to like having like physics level characteristic, then you need to go like the COMSOL for having like chemical, thermal, and if you want to do fluid models, then I think this one would be the best software. And CFD based modeling for flow and heat transfer, probably ANSYS would be the better choice. Like for optimization, if you do not want to write codes, then like Homer might be a option that you can utilize for just doing the system level optimization, where you do have fuel cell, but you have other DG and other devices as well. And if you want to do like network level simulation, either mechanical or even like electromagnetic. So, for electromagnetic, I mean probably PSK is the best option. PSSC you can use for electromechanical, where it does not involve the dynamics from power system, I mean power electronics. But if you want to capture the power electronics, then I think PSCAD is the best solution. So, again I mean depending on your research, which one I mean like more important for you, based on that you can identify which software either you or your student gonna be utilizing. And again I mean we already mentioned all of them, like the application. Now, the first one I am now going more detail about these 4 methods. So, the first one I mean as I said that it does not capture the detailed electromechanical, chemical or physical process that is happening inside the fuel cell. Instead of that, what we just do, we do some testing, we measure like voltage, current, and then whatever unknown parameter. So, let us say I mean this is like the characteristic curve. So, you might measure like output voltage, resistance, but not like all the like variable is known here. So, there you can see there are some coefficient, which is one of them related with the resistive losses, which is definitely the related with the current, and the other one the relation is like logarithm. So, if you can remember in the initial that was like exponential logarithm relation. So, you need to have some logarithmic term in your characteristics equation, and here we have got one definitely that is relevant with the current, but other one like is small constant, because sometime if you have got 0 here, you might have like singularity problem. So, that is why we just use a small constant to avoid like that singularity problem here. So, what we will do that by knowing like whatever you know here, but this K1, K2, K3 maybe you can assume, but K1, K2 by curve fitting method with the measured value and then unknown whatever parameter you have, you assume, and then you do have characteristic curve. So, by playing with that, at the end you have to make sure that the characteristic curve actually it matches with the originally characteristic curve of the fuel cell. So, that is how you are going to do the empirical model. Although it is quite simple, it is easy to implement in simulation like MATLAB Simulink. If you do not want to use the existing one, and if you want to develop it just like a simple equation, and you can easily implement it any software, and as it is simple, you are going to have like fast computation, and sometimes if you want to do real time, then you have to do like very quick calculation, right. So, if you have got like let us say you need 10 minutes, then there will be like a long delay. You might not be able to have real time control, or even like hardware in loop simulation. In that case, this model might be okay, and also might be okay for like an initial level system design initially, and then later you can finalize and optimize using like very detailed model, because when you are going to do like feasibility, you do not need exact very detailed model. Feasibility is something like that, it might be possible and it makes sense, and then later you can have very detailed model. But definitely it has got number of limitation, because when you do experiment, we do consider certain operating condition, right. So, let us say you are considering one particular fuel cell, it has got particular voltage, current and power rating, and also particular temperature that you are doing. But if something changes, that you are changing the fuel cell rating, right, or also you are changing the input hydrogen flow. So, anything changes, you have to do the experiment again. So, only that model is valid only for the condition that you have did the experiment. And as I mentioned that it does not capture temperature variation, gas composition changes, or any transient state of behavior. And as I said that you need new experiment to update the model if anything changes. So, that is the disadvantage, but good thing is that it is very simple. It does have some application, as I mentioned, that preliminary design, real time simulation, energy management, but not the control. Energy management might be okay, but control algorithm for the validation is proper, but for the initial maybe you have to consider the detailed model. And rapid performance estimation like in vehicle and stationary system level simulation. So, if you want to estimate something rapidly, this model might be okay. And the next one is semi empirical. So, semi empirical means that it does consider electrochemical. The previous one even it does not consider electrochemical. So, it considered that empirical plus that electrochemical model, and this is the equation like for electrochemical model, where again it does have these 3 losses, and this is that reversible voltage based on that thermodynamics, and these 3 losses we already talked about. So, what we did, we used this model, and then later we use that test result to see that whatever we are getting here are we getting from the test measurement, and then we need to make some changes from the model and from the experiment to exactly mimic the behavior of the fuel cell. So, it is just the combination of these two. So, that in the previous equation you see that the first reversible voltage, you can actually model that electrochemical model that I mentioned. So, this is the electrochemical model that we are just combining with that voltage equation. Now, for all these parameter there are some like given parameters, but again I mean this might vary from like one fuel cell to another fuel cell, but this is some of the parameter, standard parameter like for E0 in most of the cases like in 1.2 to 1.3. If your temperature like around 25 degree, but if changes then definitely there is going to change. So, you also know this R, which is like the universal gas constant. T, I mean that is a temperature in Kelvin, but you need, if you know like degree centigrade, then you need to convert into Kelvin by adding 273. And F, that Faraday's constant, that is also known. And this is some of the pressure value of hydrogen, oxygen and water. So, using all of this and activation equation that I already mentioned in the previous cases. So, using this, and you can calculate ohmic, concentration, all of these three like losses using these three equation. And then this is again like the constant. So, this constant sometime from your experience or even like through that experimental process you can calculate, and then you can do your model. So, again if you compare with the previous one, the key difference, the empirical is just like experiment. This is like theoretical principle plus experiment is derived from like the curve fitting, but this is more like physical laws with just some adjusting the parameter, and it's slightly bit more complex than that one, although it's not complex as the detailed mathematical model, slightly more computational burden slightly higher for this one compared to that one, but definitely that one accuracy will be higher than this one. So, this is like some of the application. If you want to do the performance analysis of different, you can use this method. Control system for fuel cell powertrain, sometime for microgrid also you can do that. In cases like you consider that the temperature and other parameter will not change significantly, then probably it's okay to use this model. Power electronics design, simulation of hybrid system like the battery fuel cell, sensitivity analysis, that like the model for particular one temperature, then if you change the temperature, humidity, how your system is behaving, probably you can do that. Again it has some application advantage mainly in terms of accuracy, but definitely there are some again like limitation as well. So, it still needs some experimental data, may not be exactly capturing the dynamic behavior like dynamic state shutdown, and also it might be simplified compared to CFD 3D multiphysics model, and accuracy depend on the quality and range of the fitted data as well. So, the experimental data and others also actually heavily contribute in the accuracy of the modeling. And then this is like the most detailed dynamic model, which is physics based model that actually captures the internal electrochemical that we mentioned, but on top of electrochemical, the thermal, fluid, electrical process in the system using the fundamental in the physical law. And this model given like very detailed insight into transient behavior, which is good for if you want to design like define robust control, and also you want to do the performance level optimization as well. Again this comparison I'm going to skip it. Only thing is that it will be more like complexity higher, computational cost higher, but its accuracy will be better than other two. For physics based dynamics model, you are considering electrochemical reaction that's happening in anode, cathode, that's also including charge transfer, mass transport. So, all of this included here. So, when I say like the charge transport, that's actually nothing but the movement of electron and ion. So, if you remember that in the previous class we did mention that where proton, electron, they are actually passing from either anode to cathode or vice versa. So, that's charge transport or that's ionic and electronic conductivity happening within electrolyte and electrolytes, that actually included in this model. And also the mass transport, that's considered the transport of reactants like hydrogen, oxygen, and also product like water within the fuel cell, including like diffusion, convection, all of them actually consider. And we also do consider heat transfer mechanism like conduction, convection, radiation, and that's actually happen in the real system. So, that also include in this model. And all the losses like the voltage losses, that we mentioned already, that's 3 losses that do consider to predict accurate cell voltage, and the temperature, pressure, reactance flow, all are considered, all operating condition considered here. And also it does model the transient behavior of the fuel cell, like if you have like load changing, which is also good for understanding and controlling the fuel cell system. Now, in terms of mathematics, we already explained that electrochemical dynamics, the same equation, that's we consider the semi empirical model, but on top of that we do consider the mass transport dynamics, which include like the gas flow rates, diffusion through gas, diffusion layer, and then reaction consumption at catalyst layer, and that's how actually we use that balancing equation, using the charge in and out, the voltages, and here I mean these are the parameters you need here, like the sorry, this one actually for this equation, but for here only common thing that you need to know the Faraday's constant, but charge in and out, that actually need to model that, but this is again like the single dimension, but it can be also like in many cases people use like 2 dimension, 3 dimension as well, but in most cases single dimension is more than enough. And then you do consider charge transport dynamics, that's I mentioned like in previous cases that electrical and photonic conductivity, we also consider membrane potential and the current density. Using these 2 equation, you can use the charge dynamics, and then for thermal, again for thermal you have got heat generation, heat losses, and then whatever in the heat actually loss and generation, and the difference if it is like steady state, then it's gonna be 0, otherwise that difference actually give you that the changes in the temperature, temperature dynamics within that particular system. So, it does involve like electrochemical reaction, home heating, and heat losses to the surrounding, and these are the parameter you need to model that thermodynamics, like mass of the fuel cell stack, specific heat capacity, cell temperature, total heat generated, and total heat losses to the surrounding. And why actually thermal model is actually important, because if you want to optimize that operating condition like temperature, flow rate, then we need that thermal modeling. even if you want to design control system that works like in defined work environment. So, let us say you are having that fuel cell in the system where the weather is cold, and if somewhere you place the fuel cell which is like have hot weather, right. So, if you want to make sure that it works for the different like temperature, then you need that model to consider in your control design system. But if you think that the control that you are designing temperature will not change that significantly, then it is okay to neglect that one. And also like the component sizing and selection for your cooling system, like radiator pump, and if you want to determine exactly there what size of pump, what size of radiator you need for a given fuel cell system, then you need that thermal model. And if other thing, if you want to predict the degradation, because like the battery, fuel cell, whatever you have, with respect to time, its capacity will deteriorate. And if you want to predict what might be the outcome you get after 5 years, then also you need to have this modeling included in your overall system. And even like the system level integration for larger like vehicle, stationary power plant, thermal model will give the more accurate performance for your design controller. So, that is thermal model, as already mentioned, like that that heat generation, it might happen through your electrochemical reaction, and also losses, heat transfer like conduction, that is already might be within the stack and the cooling system. Individual component like the membrane, electrodes, bipolar cooling system are also needed to capture the thermal behavior. And depending on again like either steady state or more dynamic you prefer, based on that you need to decide either you are gonna consider like constant temperature or like the variable temperature. And as I mentioned that it could be like one dimensional, two dimensional, or even third dimensional, depending on like if you just consider variation like one direction, often like how the gas is following, then one dimensional might be okay. But if you consider the variation in two direction, then in most of the cases one like perpendicular to the gas flow, then you need the two dimensional. And three dimensional, if you consider temperature in all three dimension, then you might need three dimensional model. And here some of the applications I already mentioned like most of them, that you need to consider this type of model. And the final one, we also need like water humidity management system. It does consider these few things, which mostly economical, important when you do that PM fuel cell. Now again as it has got differential equation, so that means it will have like your state variables. Now if you consider the most simplest one, it has got 5 state variable, that means 5 differential equation, and this state variable that hydrogen concentration at anode, oxygen concentration, membrane hydration level, temperature, and cell voltage. And this typical 5 equation, that is going to give you this 5 state variable. But here again we have number of things that we make assumption, but using that one but if you say that you are not going to make any assumption, then it might be like 7th, or it might go 7th or 8th order model, which even would be like more complex. But in most of the cases, this simplified dynamic model where we have got 5 differential equation, that's might be okay to have your overall system model. Like again this using state variable, using that hydrogen mass balance in the anode, where you do have like the flow rate, which is denoted by the Q, flow rate in, out, and then your anode compartment volume V, cell current and Faraday's law. Using that one, you can actually model that hydrogen mass balance in the anode. And then next one, oxygen concentration. So that one, oxygen's balance equation, again I mean quite similar. You have like only oxygen in and out instead of the previous one like hydrogen, because in the anode we have got hydrogen input, in the cathode we have got oxygen input. So only the difference, this is the cathode volume and previous one it has got anode volume, but other than that all other parameters quite similar. And then for membrane water content dynamics, that's given by this equation, where this one just like a constant coefficient, this is another constant, and this one equilibrium membrane water content. So using that lambda, like this is we consider constant, but this lambda is variable, that in water content dynamics. So we can use that equation to model the water content dynamics. And then thermal dynamics, again this is like the single dimensional model, where you consider the heat generation and heat losses, and you need the mass and heat capacity, and using that one where T is the variable here, temperature. So that's how you can model the thermal dynamics. This one we already mentioned in the previous cases, the cell voltage, which is semi empirical, we already discussed this model. So using that one, you have got the cell voltages. Now to model that, finally you need these parameter, which you might get some of that when you buy the fuel cell. Some of the parameter might be given in with the product that you buy, and in many cases if not, then you might need to do some experiment or other way, you have to make some assumption, then you can have the overall model. And then like as I mentioned, the control design, it could be like a simple PID, or even like if you want to go like very robust like model predictive control, or there are also many like other robust control technique as well. So if you want to go for those sort of control, this model might be the best one. System level management model, and for educational purpose, this is also you can use it to find out exact the system. Now if you want to practice this, these are the some of the like typical values given, just for this modeling purpose. If you are interested, you just go like MATLAB or other software, use this parameter, and then you play with that one. And then the final one, so as you know that like as a electrical engineer, we always interested for equivalent circuit. Like if you think about like electrical machines or electrical generator, transmission line, even what we do, always we use like equivalent circuit, for like doing analysis and different other studies as well. So this one we try to relate using that voltage source, resistance, inductance, capacitance. Using that one also we do have the modeling. So you can again here that either fuel cell or stack level, in the model you will find 7, 8 or even more than different types of model. Even you can just get it for here, but again in many cases people just use in many cases like one resistor here capacitor and one series resistor. That's actually in many cases quite enough actually to model the behavior of the fuel cell. And definitely I mean if you have got converter, inverter, you need to also model those part as well. But here I just included the fuel cell stack and the one like buck converter. We didn't consider the inverter. So using this one, I mean just applying KVL, KCL, like for example here for the voltage, like that that reverse voltage and that the losses that we mentioned, these three things with the reverse. Actually this is the same equation, but only just using V instead of E. So we can use that for like the voltage equation, but for like other cases, for example here, if you see like in the very like the right hand side, so if you consider this loop, right, we can easily apply KVL here. So how many voltage we have got? This voltage and this voltage, right, 3 voltages. So using that KVL you can easily relate these 3 voltages. So when you have got like inductance, so here we have got inductance capacitance because we did consider the DC to DC converter, and this is actually coming from DC to DC converter. So using capacitor, inductor, I believe you know how to calculate the voltage L di by dt, and from that you will get the this current. And once you know this current, if you consider this node, you can apply KCL where you have got 3 current, right, this IL, IC and electrolyzer current. So if you relate these 3 current, you can easily then represent that IC using that capacitor voltage equation, and then is just by doing some simplification. That's for the right hand side. If you again then apply in the left hand side, I'll finish the KVL in the loop, then I mean you can get this equation. Now again I mean if you apply KCL, you will get this 3 current. So what I am saying that by just applying this KCL, KVL, this is very simple. I think every one of you know that. But after that, if you want to have like the state space model, I believe you already all of you know like this is the state vector, A vector which is related to state variable, and the B matrix related input control. This is the measured output matrix. In most of the cases, I mean you might get 0 here. So by doing that, I mean finally I have given like all the matrices here. So you can find all the metrics, and as you know that once you have this state space model, it's very easy to do other study. For example, if you want to do the, let's say eigenvalue analysis in MATLAB, if you just write EIG of matrix, this one is going to give you all the modes and eigenvalue. That's going to give you that whether the system is unstable or unstable. Even if you do number of like control doing the transfer function, if you want to do like different types of plotting, from that one if you want to tune your either PI or PID control, you can do actually many things once you have this mathematical model and the transfer function. So one of you already mentioned the previous time that how we do the maximum power point. So this is like your voltage, right, and this is current. So if you multiply like the voltage and current, you're going to get the power. So here this is maximum voltage, but the minimum current. So, you will get minimum like the power, and then in different points if you multiply voltage and current, your power curve will be like this, right. And then you are going to find at what point I am going to get the maximum power, and then your MPPT control. Again, I mean, for MPPT there are different algorithms that you can use to find out exactly the maximum power point, but in many cases what we do that we make some changes in the voltage and we see that whether power is either increasing or decreasing. For example, if it is here, if you make changes, it is going to increase, but after going for maximum, if it changes, is going to be reducing. So, that changes is either positive or negative. That is how you can find the maximum, but there are many ways, and recently people are using even like AI and very advanced level of control technique for MPPT control as well. And later, I mean, if you want to find out that characteristics by having the sensitivity analysis, for example, if you change the fuel level, how that IV curve is changing. So, here you can see that like 100%, 80, 60, 40, how that characteristic curve going to be changing, and you see that for every curve if you do MPPT, it going to be actually different. Same for like if the current density changes, how it changes the voltage, different voltage, that also I mean you can do from that simple mathematical model. You can also do like if for example changing the temperature and pressure, how like that relation is changing. There will be some changes, but as I say, like in many cases if that changes is not significant, then I mean you can make the temperature constant. But here you can see that if you change temperature, pressure, your voltage, current and the output power going to be changed. Same here like current density, and we also compare like few different model just to see like the difference between the one that we tried and the other people tried, but you see that is quite close, although there are some differences. Now, here I will finish this one, but only one more like an application. So, here you can see that we have got 6 different model, and for all like the first one like the full model that include the thermodynamics that we mentioned, it's a highly nonlinear logarithmic dependence VSLI, and then for next one we did consider some constant, because here the problem is that the data availability, as I say that it's not easy to get all the data that you need to model that very detailed, and then we have got third, fourth, fifth and sixth model. So, this is the first one, how that other model looks like. I have given here like the third model, fourth model, fifth model and sixth model. Here you can see that. So, normally like people try like in the fourth level one. So, here you just have like one series and one parallel combination of resistance and capacitance. So, what I am trying to say that even if you consider all the dynamics, if you sometimes neglect some dynamics, if you and just to doing that, I mean although you are going to be talking about the control system later, but again I mean for doing that simulation we did consider like the overall fuel cell control here, where you can see that because it's grid connected from PLL, we measured like the angle and then we use that one for active power control. Then we from voltage we have got reactive power control, and then current control as well, and how this control here I have shown like, although I mean we are going to be talking all of them later, but where I am saying that using all the control, and initially we just try like very simple model that like a single machine to infinite bus, and then we tried like what's the difference like if you have like a simple model only single machine to infinite bus, And here you can see that when you think like the voltage and current, you can see that some of the cases you have got very high voltages, but in some cases like when you consider all the losses. So, if you consider the first one, it did consider all the losses, then your voltage is going to be lower. But the other cases, when we do not consider the losses, you might get the voltage higher. But what I am trying to say that when you have got the current, although I mean the amount is not significant, but whichever has got the lower voltage, you will get the higher current. But what I am trying to say at the end, if you measure the power, there is not that significant difference between all the models that I mentioned. So, if you are not that much interested for temperature variation, pressure variation, other things, then what I am trying to say that if you are just more like the power level interested, then if you just use the simple model, it's actually it's more than enough, and it is going to give you almost accurate behavior for all the things here. We tried voltage, power, frequency, and we haven't found any like significant difference of the response that we get from there. So, maybe I will stop here because we want to have a tutorial. The application I already mentioned, and also you can read the slide as well. So, with that I will stop here, and then now we will try to connect for the tutorial, but at the same time I am here. If you have got any question, you can talk later, but you can try to connect now.
Thank you, Professor. So,
well, again power transient like voltage and power, that is actually more than enough. We did number of, even like the control also was fine for voltage, but if you are more interested that I am going to be seeing like how the pressure, temperature and other things changes, and that's I want to include it in the transient, then probably you need that model, but only for electrical output power, it is actually more than enough even for transient analysis as well.
Eigenvalue analysis if we have to go for.
The eigenvalue again, because eigenvalue analysis, what we consider for eigenvalue, we consider a very small step change, right? So, that's almost like many of the parameter is almost like constant. So, that's simple, the parallel resistor capacitor with the series resistor is more than enough to do eigenvalue analysis.
Okay. So, the equivalent model can be a better option, sir?
Sorry?
Equivalent model, the last one what you said, equivalent circuit model can be a better option?
Yes, that would be like a more than enough.
Option. Yes. Thank you, sir.
Because it's comparatively simple, because what happened like if you want to do some eigenvalue analysis, and then you have got the modes, right, and then from modes you find whether stable or unstable, and then for that if it is unstable, if you want to design the control by doing the participation analysis, that which factor is contributing, then when you have got so many parameters, sometimes it's not easy to find out. So, yeah, so in that cases, yeah. So, what do you say lastly? Yeah, that's right. Yeah.
Sir, can we use the semi-empirical model for the MPPT?
For MPPT significantly, then probably you can use that one. But if you see like that, very like the variation is very large, then probably it's better to go for like other model. But if you have like a change, there is a change, but it's not that significant, then probably it's more than enough to do empirical model for MPPT.
Because sir, whatever the polarization curve we obtain in the MATLAB, right, in a semi-empirical model curve, so it will be exactly same. We can correlate with this
That's right, because even if it's empirical, but you are actually comparing with the, I mean, the ideal condition one, right? And you play with and how much, I mean, how much error, I mean, you can reduce by changing those parameters. So in that case, I mean, yeah, you can do that. Yeah.
Thank you, sir.
Yeah.